Hello and welcome back to Stats 2. In this lecture, we are going to talk about the basics of contrast coding. Contrast coding is something that we have to do whenever we are dealing with a categorical predictor variable. For the sake of a simple example, we could imagine that we are doing a reading experiment and we have a predictor variable with two levels, a categorical predictor, and say we are examining, as so often mentioned, the difference between subject and object relative clauses. So we have the level subject relative clause and the level object relative clause. And now the question is, well, we want to plug this into a regression model somehow. So if I have a continuous predictor, it's very straightforward. So if my diagram looks like this, that here I have the dependent variable and here I have the predictor, then if the dv, okay, let's assume this one is continuous anyway. So this one is continuous. And if our predictor was continuous, which it's not here, but say for a moment it was, then we would have a very straightforward scale. For example, if the predictor was the age of the participant, the predictor would be a numerical value, which represents years of life, for example, and then you could plot the data points on this 2x2, on this two-dimensional grid. But when the predictor is categorical, meaning that it's not numbers, it's like categories, subject relative and object relative, then it's a bit less clear how we can plot it here. And we need to plot it here somehow, because in the end we want to fit the best fitting line, remember, for a linear regression, or for any other kind of generalized linear regression for that matter. So we need to find a way to represent our predictor as numbers, okay? And even if it's actually categories, we need to find a way to convert these categories into numbers, or to think of these categories as numbers, okay? And an example would be to say, okay, we're going to give the subject relative clause the number 0, and the object relative clause is the number 1. And then we could say, okay, there are data points at the 0, which actually represents our subject relative clauses. And then there are data points at the 1, which represent our object relative clauses. And so here now we would have some data maybe here, and then some other data points here. And that's now a situation where we can again plot a best fitting line, and also actually find it mathematically when we fit a linear model. And basically the art of picking suitable values for our categories to represent them numerically, and also to decide, well, which particular values I will pick and what the consequences are for how I will interpret the resulting linear regression model, that is what contrast coding represents. And in this basic lecture on contrast coding, we will see different examples of very common contrasts that are used in statistical modeling. An important fact about contrasts is that there is not only one possible way to assign numerical values to a categorical predictor. In fact, oftentimes there are multiple possible options to choose from. And we should not take this lightly and just pick any of them, or the one that we are most familiar with, because which numerical values I pick to represent my predictor variable actually matters. In the sense that depending on which values I pick, I am basically encoding slightly different hypotheses about the predictor and its effect on the dependent variable. So for now, let's note down that contrast coding is closely linked to the hypothesis, or possibly multiple hypotheses, that I want to test about a specific predictor. But this may still seem a bit abstract and unclear why that should be the case, so we'll now unpack this step by step. Let us start out with an example. In R, you have a range of default data sets available to you, which are like real experimental data from some famous experiments, which you can use to like use them as examples for conducting statistical analyses on them. And one of those data sets is called tooth growth. So you can literally just access it as a variable in R, and it will be a data frame that's already ready for you, okay? And this tooth growth data set basically is from a classical study from the 1940s in which a researcher called Crampton took a sample of guinea pigs and gave different guinea pigs in this sample of guinea pigs different doses, like different magnitudes of doses of vitamin C in particular, okay? And he wanted to find out if the doses, so the doses is the categorical predictor here, in that there are three levels. There's a small, medium, and a large doses. And so the question, or the possible relationship is whether which doses, if it's a small one, the medium one, or the large one, if this has some effect on the tooth growth in these guinea pigs, because there are certain cells that are responsible for tooth growth, the so-called odontoblasts, and when these are longer, that means there is bigger tooth growth. So the dependent variable in this case would be the length of odontoblasts, okay? You can just think of it as tooth growth, I guess. And so this is the dV, which is continuous, and this is our three-level categorical predictor. And so now the question is, how do we encode this three-level categorical predictor using appropriate contrast coding in order to test certain hypotheses about this potential relationship? And one possible pair of hypotheses that I could have about this relationship would be the following. So I could say that I have a first hypothesis, which is, well, I can call it H1, and this states that when the dose of vitamin C is small, then this should result in less length of odontoblasts, like less tooth growth, than in the case of a medium dose. Would kind of make sense intuitively, at least, right? And if that's my second hypothesis, I have a small dose of vitamins, then this should also result in a smaller length of odontoblasts than in case of a large dose of vitamin C. Now, note that I could also have other hypotheses about this relationship. This is just one possible pair of hypotheses I could construct. For example, in this case, there is nothing mentioned about the difference between medium and large. Like in this case, it's all about small as a baseline compared to either medium dose or large dose, okay? And now let's first focus on these two hypotheses, because we will first see which kind of contrast coding we can use to, well, encode this predictor variable, this categorical predictor variable, in such a way that specifically these two hypotheses are tested. And later on, we will see how we can modify the contrast coding in order to test different pairs of hypotheses here. So here we have RStudio. We can just have a look at this dataset tooth growth using the structure str command. And as we see here, there are, well, actually three columns in it. Len, which is our dependent variable, length of odontoblasts. There is another column, supplement, SUPP, which we will ignore for now. For simplicity, we'll just look at this single predictor dose here. Notice that here it actually also appears as numeric because it's specifically the dose in milligrams per day. But for our purpose, we want to really think of this as a categorical variable. So we'll have to figure out what the unique values of this variable are. And as it turns out, well, there is 0.5, which is our small dose, 1.0, which is our medium dose, and 2.0, which is our large dose. And let's just quickly convert them to a factor in order to really treat this as a categorical variable. So you'll forget completely about the specific quantities in milligrams per day and really just think of it as a categorical variable with 3 levels. So in order to do this, we will recode this. Maybe I'll first save this data frame in a new variable called d, like I'm creating a copy of it. And in this copy that I've created, I'll assign dose to be a factor, which is how we typically encode categorical variables in R by default. So let me do that. And now this factor, if I look at its levels, it still has like odd names, which is just strings containing these numbers here. I want to rename those to my actual like verbal descriptions, small, medium, and large. So I'm gonna change the names of these levels to small, medium, and large respectively. So I can check again. And indeed now I see these levels here. And here, when I let R print out the levels of this factor, I see that the first level is small in the way I've specified it here. This is good for me because, as we will see in a moment, R will assume automatically a contrast coding in which small is the reference level to which either medium or large are compared, exactly as the hypotheses that I've specified here would want to happen. If by any chance I wanted another level as the reference level, for example, I want to compare medium to small and also medium to large, in that case I would have to make sure that I will put medium to the front here to be the first level of this factor as defined in R. I could achieve this using the relevel command, so I could do ddose should be relevel of ddose with a new reference category, a new reference level. In this case, the one that I want to have first, so that will be my reference. I could put medium here. Then if I would do levels of ddose again, I would see that now medium is in the front, but here, as we saw, we actually want to have small in front. So let's revert that to have small as our reference level. And so now everything is back to normal as we want to have it. Now, before we actually uncover what the contrast coding will be in this case and how this will look like once we run a linear regression using this variable dose as a predictor, let's maybe first remind ourselves of what we actually want to compare and what kind of differences we want to look at and basically see if they are relevant or not. So in this case, we see we have a difference between small and medium or a difference between small and large. Either way, what we will need is the group-specific averages of the length of odontoblasts, right? That's what we are practically comparing. And if they are very different, then we hope that our test will reflect that and see that there is a significant difference in the length of odontoblasts. So as a first step, it's always a good idea to maybe just look at this descriptively without applying any inferential statistical test or linear regression, and just, take the subsets of this data set and see what the mean is, like the sample mean for a specific group, for example, only for the small dose cases or only for the medium dose cases and so on. So what we could do is we could say we want to have the subset of our data set D where the dose is equal to small, and on this subset we then want to take the length, so the tooth growth, basically the length of odontoblasts, and see what the mean of this particular length is in this subset of data. So we can run this and we see, okay, so for those guinea pigs that just received the small dose, the average length of odontoblasts was 10.6, whatever the unit is, I'm not sure, but something, okay? And we can do the same thing for the medium group. So we will replace this to medium and we see, okay, for the medium group, the average length of odontoblasts was 19.7. Same thing for the large group. We see that here the average was 26.1. So just looking at this descriptively, without any statistical test applied yet, we can see that, okay, maybe there is some relationship indeed, that, the larger the dose, the bigger the length of odontoblasts. And, well, what will we compare in the end? So we will see if the difference between small and medium, if that is non-zero. That's one of our hypotheses we want to test. So we could, in effect, say, is this average for medium? I'm just retyping it here out of laziness. Is this 19.735? If I take this minus the average I had for the small dose group, is that number significantly different from zero? That's what my hypothesis 1 is about. And my hypothesis 2 is about whether the difference between the large average, so 26.1 in this case, minus the small dose average, so again 10.605, if that number, so a difference of 15.5 units, if that is significantly different from zero. That's what my hypothesis 2 is about. But again, this was just the descriptive quick look at these data. We have no information about the variance, so we really can't conclude anything from just looking at means and nothing else. And really, the only conclusions we can draw is once we have run inferential statistical test, for example, by fitting a linear regression on these data. So let's do that then. We can take the simple linear model, like here we don't have hierarchical data, so we're just dealing with a simple linear regression, not mixed effects one, okay? So what we can do is we can say, okay, we will create this linear regression model, which we'll save in this variable m using the lm function, and our dependent variable, as we said, is the length of odontoblasts, and then the tilde symbol, and then we want to define our predictor, which is the dose. Likewise, I could write 1 plus dose, which makes it more explicit that I'm also estimating an intercept and also a slope for dose, but actually these two are equivalent. This is just a shorthand for this notation, okay? And we can do that, and obviously we also will have to define where our data come from. In this case, they come from this data set which I've saved in the variable d. So with that, let's fit this small simple model. I'll just press enter, and now we can look at the summary of this model. In this model output, which I've made a bit more overseeable here, we can see different things. The most important things I want you to focus on is the estimates for the intercept and then the estimates for two different kind of slopes. Okay, the dose medium slope and the dose large slope. In fact, by default, if we don't specify anything else, R assumes so-called treatment contrasts when we are providing a factor like a categorical variable with 2 or 3 or more levels, which means that R will treat the very first level in the factor, in this case the small level, as the reference, and in the output of the linear model, the intercept will correspond to the average of that particular level, more or less. Okay, so here we have an estimate of 10.6, which was indeed roughly the mean that we also saw descriptively for the group of guinea pigs that had the small dose. And there are two slopes here now. You recall we have two hypotheses, so there are two different slopes, each of them also assigned with a particular p-value in this output. We'll get to this in a moment, but okay. And here the first slope is about this hypothesis 1, where the estimate here is now the number of units we will have to add on top of the baseline level of 10.6 for the small dose in order to get to the average value of the medium dose. So this represents the difference basically between medium and small. Okay, so it says the medium dose is about 9.1 units, leads to a result which is about 9.1 units higher on the dependent variable, length of odontoblasts. Likewise, this slope dose large now represents the difference between the large and the small average, meaning that here we have 15 units roughly that we will have to go up in order to get to the average roughly of the large dose group. So just from this output we can basically read off in summary that the average for the small dose, which is our reference level, is about 10.6 units, whereas the average for the medium level will be 10.6 plus 9.13, so roughly 19 to 20 units. And the average for the large dose will be roughly 10.6 plus 15.5, so about 25, 26 units. As a quick side note, maybe you have wondered where these t and p values in this output for the linear model come from. So you can already see it's doing some kind of significance test, but perhaps you will be rightfully puzzled by this, because 2 weeks ago we talked about the fact that we need a likelihood ratio test to do a significance test for a linear model, or also for a linear mixed model for that matter, by fitting two models, right, one with and one without a certain parameter, and then computing the -2 times the log likelihood ratio test statistic and looking that up on a chi-square distribution and so on. But here, interestingly, we see a t-value, suggesting that here there is some t-test being carried out, and a corresponding p-value, which is, well, derived from checking the corresponding t-distribution. And in fact, yes, there is an alternative to the likelihood ratio test, which is these t-tests on parameters in a linear model, or like fixed effect parameters in a linear mixed model. It's a bit more tricky to unpack than the likelihood ratio test. That's why we're not going to look at this in detail, how the t-test within a linear model or a linear mixed model works. But that is in fact what you will see in the standard summary output, either of the linear model or also of the linear mixed model when you use the Elmer test package. And for our purposes, we can just treat this as the output of a significance test. That's also usually the kind of values that you will see reported in papers, where they will report the t-value for a particular predictor in linear model or linear mixed model, and then the corresponding p-value as well. And if that is below 0.05, then it's significant. That said, it's always a good idea to check if you get the same results using a likelihood ratio test. Most of the time, they will yield the same conclusion. There might be exceptions, but I guarantee you that might be a good exercise for you to try if you were to probe the significance of either of these parameters, so like the intercept parameter or the slope parameter for hypothesis 1 or the slope parameter for hypothesis 2, using a likelihood ratio test, as we looked at it 2 weeks ago, then you should find the same result, meaning that for all of these three parameters, we should again see a significant result, right? Meaning that each of these parameters is likely different from 0, so including it matters. All right, so we've clarified this, we've seen the model output and understood how we can interpret it in light of this idea that we have picked one reference level, which is now represented by the intercept, and how the changes with respect to the reference level are represented by these two slopes. But we still haven't seen the contrasts. We still have not seen what contrast coding is assumed here underlyingly which results in these results with this particular mapping of the reference level represented by the intercept and the differences represented by these two slopes. How can we see the contrasts? We can use the so-called contrasts function in R. So we can, let me put this back to the right here, we can run the command contrasts on our particular variable of interest. So in this case, the dose variable, which is our categorical factor that we care about here. And this will give us the contrasts that have been assumed here for this particular variable. So let's unpack this. We see that it's sort of, you can think of it like a matrix, like we have this contrast matrix. And here on the left, for each row, we see the three different levels of our variables, small, medium, and large. And here as columns, we see, basically you can think of it as artificial numerical predictors. And here we need two of them, actually. One of them is the one that will correspond to this dose medium slope. That's the one in this left column here. And the other one will correspond to this dose large slope that you see in this output. And so basically we are transforming this categorical predictor with three levels into two artificial numerical predictors, namely the one that is about the difference between small and medium, and another one which is about the difference between small and large. Okay, and so the idea is that each data point, for example, if it is a data point belonging to the small level, then it will have these values for these two artificial numerical predictors. So any data point regarding a guinea pig which received a small dose of treatment will have 0 as its value for this numerical predictor regarding hypothesis 1, and will also have 0 for this numerical predictor regarding hypothesis 2. Okay? Whereas if we have a different data point, for example, a data point regarding a guinea pig which received a medium dose, this data point will still have 0 on this second artificial numerical predictor, but it will have a 1 now for this first, the left column numerical predictor, which is about the hypothesis 1, comparing small and medium dose effects. And likewise, we will also have data points which represent guinea pigs that received a large dose, and so these will be assigned a 0 value on the numerical predictor which is about the slope representing the difference between small and medium, but a 1 on the numerical predictor which represents the difference between small and large. These kinds of contrasts are also called treatment contrasts, or sometimes dummy contrasts. The reason they are called like this is that they apply to particularly the kinds of situations where you have some reference level, for example, the small dose, okay, and you want to compare different kinds of treatments, like different drugs, let's say, or in this case, different other sizes of doses to that baseline level, to that reference level. So that's why they're called treatment contrasts. You could also imagine that you have some people with a disease and you try 2 different drugs on 2 different groups of people. So these are 2 possible treatments. And also there's another group of people that don't get any treatment, so they will be the baseline or the reference, or they will get a placebo or something. So always when you have this baseline level, and then you have some other levels, or treatment levels, which are compared to the baseline level, always to the same baseline level, that's when these treatment contrasts are useful. It's debatable if here the treatment contrasts comparing only small to medium dose and small to large dose, but there is no comparison between medium and large, if that's the most sensible thing to do in this example. But we're doing it here for the sake of the exercise, because these are the simplest kinds of contrasts we can apply. Now, you may wonder, so you've seen these numbers here, that we basically create these artificial numerical predictors with the 1s and the 0s, but I don't blame you if you don't see the connection yet of why defining those numerical predictors in this way will lead to the properties that we saw above here, namely that the intercept now represents the average value of the dependent variable for the reference group, in this case small dose, and why these slopes here represent exactly the differences between small and medium or between small and large. Like, this is not obvious by just looking at these numbers. So let's unpack this now carefully, how this kind of contrast coding indeed leads to the expected behavior that we saw in the example here, that we can interpret the intercept and the slopes as I just mentioned. To do that, it would be useful to understand what this linear model that we've fitted here represents mathematically. So let's try to write this down as a mathematical formula instead of this syntax that we give the lm function. So to do that, let's maybe relabel some variables. Let's say this length, which is our dv, maybe we can just call it z, okay, for the purpose of our mathematical notation. So len is now z. And here we have these two artificial numerical predictors, which basically define how we contrast code this three-level categorical variable. So this medium, I'll just call it x, okay? And this other artificial numerical predictor, like the other component of this contrast coding, let's just call it y, okay? So with these variables defined as such, we can now write down the formula of precisely what we predict a particular data point of the length of odontoblast, in this case z with some index I representing a specific guinea pig, a specific data point, how this comes about basically, okay? So this z is equal to, well, first of all, some intercept, which I can call beta 0 here. And to this intercept, we add beta 1, the first slope parameter, which is multiplied by our variable x. So in this case, beta 1 times xi, which represents, this artificial numerical predictor for which only the medium data points get a 1, but the other ones get a 0, okay? And then I'll also add beta 2, which is now another slope, which is multiplied with this other artificial predictor, which is now the one where all the large data points get a 1, but all the remaining ones get a 0, okay? So I will write down the formula like this, and then obviously there's, as always, some residual variance that is not explained by this linear relationship. And so now let's look at each of these three levels and try to understand what this equation simplifies to once we assume that we are in one of these three situations. So let's say we have a data point for which the dose is small, okay? So if the dose is small, this means that this x predictor has value 0, and also this y predictor has value 0. In other words, we would write that zi is equal to beta 0 plus beta 1 times 0 plus beta 2 times 0. I'm leaving out the residual term now for simplicity, but you can always imagine it there. So basically, if I multiply something with 0, this means that I can just delete it, right? It will just be equal to 0. So I can delete this, and what I end up with is that this data point will now be just equal to the intercept. Obviously, again, plus some residual variance, but the prototypical small dose data point will be predicted to be just equal to the intercept, which is what we saw in this output, right? We saw in the output that the intercept was exactly equal to, or more or less equal to, also the descriptive mean for the particular subgroup of data points with the small dose. Now, let's go to the second level. What happens if the dose is medium? Well, if the dose is medium, that means that our x predictor will have a 1 as its value. So we would have to write plus beta 1 times 1, whereas our predictor y will still have a 0. So this would be beta 2 times 0, again plus the residual term. And here this simplifies to, well, I can delete this part of the sum where it's just something times 0, and also beta 1 times 1, I can also write it in a simpler way as just beta 1. So I see here that the prototypical data point where the dose is medium will now be equal to the intercept beta 0 plus the slope beta 1, okay? And this is exactly matching what we also saw in this linear model output, namely that when we take the intercept, which as we now know represents the average value for the small group, for the baseline group, plus the value of the slope that we get here, namely 9.1 in this case, when we sum those together, so intercept plus slope, which gives us roughly 19 or 20, this represents the prototypical, or like the average data point that we expect for a guinea pig where dose is medium. Like this would give us the average length of odontoblasts for this subgroup. And very analogously, we could think of the case where the level of this dose is large, because in this case, well, instead of adding the beta 1 slope, we would now add the beta 2 slope, because now the y variable would be equal to 1, but the x variable would be equal to 0. So in this case, the only adjustment we'd have to make is to write that now the prototypical data point, or the predicted data point basically for the large level of this factor would now be, would consist of basically adding the intercept, which is again the average for our baseline group, plus this slope, which we have estimated. And this slope will be then logically the difference between the large group and the baseline group. And again, this also matches our results here, where we could derive the average, the predicted average length of odontoblasts for the large group by just adding the intercept, in this case 10.6, with this slope beta 2, in this case 15.4, right? So that's how we can connect the dots between this contrast coding, like this kind of maybe at first glance arbitrary matrix of zeros and ones, and this underlying logic of the treatment contrasts, where we have basically now this linear regression with these two artificial numerical predictors, which together, this x and y, is now our encoding of our actually single categorical predictor with 3 levels. All right, so we've seen how treatment contrasts work for a 3-level factor. That's actually already quite complex territory. We can, for now, maybe go a step back and make it a bit simpler and think about treatment contrasts for a 2-level factor, because we can, just as we can do a treatment contrast for a 3-level or a 4-level factor, the simplest case and maybe the most intuitive case to grasp is the one where we have just 2 levels. So let's see another example where we have 2 levels and try to understand how the treatment contrasts work in that case. In the LinkPsych package, we have different kinds of data sets available, and one of them is a sort of small little dummy data set with a few data points that just illustrate, or like can be used to illustrate how contrast coding works for a simple 2-level factor. In order to load this data set, we can use the command data and then give it the argument in quotation marks df_contrasts1. This will load our data set. It's now loaded in the variable df_contrast1. And it's not a big data set, it's our data frame, so we can just display it all at once because it just has 10 entries. There they are. So this assumes that we have some categorical variable. In this case, we can call it f. And f has 2 different levels, f1 and f2. Okay? And we have also a dependent variable, which is a numerical variable. And the relationship that we might be interested in obviously would be if this dependent variable can be expressed somehow as well, a linear model where the predictor is an intercept and also this predictor f. And now the idea is, how do we code this categorical predictor, which in this case is just a simple two-level factor. So we have two levels, f1 and f2, right? Whatever they are, subject versus object relatives, you can make anything up. It's really just a small artificial data set to practice this idea in general. Now, the idea is that, as I also hinted at the example in the very beginning, for treatment contrasts, you would encode one of them as 0 and the other one as 1 simply, okay? It's kind of the same idea as for the 3-level case, only that here it's much simpler because we just have to create a single artificial numerical predictor and not two of them. And the baseline, the reference level, will get the value 0, and the treatment level, in this case f2, will get the level 1. So you could think of an example where this is like a sensible contrast, maybe where the f1 is receiving a placebo and f2 is receiving an actual chemical drug that is supposed to do something and maybe improve your health, and the dv is some numerical measure of your health. And in fact, these treatment contrasts are also what R assumes by default, as I said. So if we don't specify anything else, we can check what the contrast coding is now for this data set and particular variable. And as we see, indeed, it's coded just as we wrote here. So the F1 level here by default is assumed to be the reference level, the baseline level. So it gets the 0, and hence in the output of the model, the intercept will be the predicted average for that level. And the other level, F2, gets the 1, just as we wrote here, because that's supposed to be the treatment level here. And so we will get a slope in the model output, which will represent the difference between F2 and F1. And if we add the intercept and the slope together, sum them together, we will get the predicted average for that level of F2. So here we could again fit a simple linear regression model using the LM function, where we say our dependent variable is now, well, literally called dv in this small artificial data set. And we want, tilde, and then we want an intercept and slope from one predictor, in this case, this artificial predictor, which is replacing the categorical values by just 0 and 1, respectively, for each level. And this is called, well, it's called f, and so here we have the actual level names, but under the hood, it will apply the contrasts that we see here, okay? So we write this, and then obviously we specify also what our data set is that we want to draw these data from. In this case, our data set df contrasts 1, and we can fit this model. Now, before we see the results, maybe we can again think of this as a mathematical formula. So we can say that our dependent variable, in this case, we could call it y simply, and our single predictor, which is just this converted from categorical to numerical predictor, which is just zeros and ones, depending on which category I'm in. This one I can call x, okay? And so with these two, maybe let's make it a bit prettier. So with these two variables, I could write down a model formula again. And so in this case, it would be just the formula that yi, which is now my dependent variable, is equal to beta 0, the intercept, plus beta 1 times the value of this predictor x, which is zeros or ones, depending on, well, the level. And then again, obviously, plus some residual variance. So here I can distinguish two situations. Well, if f is equal to f1, like if it's on the level f1, in that case, my dependent variable should be equal to just beta 0, because this term here becomes contains a 0 in the multiplication because x in this case is just 0, okay, plus the residual term, of course. But if f is equal to f2, in that case the expected, well, the predicted value for the dependent variable y should be beta 0 plus beta 1 times 1, which I can just as well delete because times 1 is just doing nothing. So it's beta 0 plus beta 1, plus the residual term, of course. We shouldn't forget that. But so what we can read off this is that in case where f1 is the level, we will just get the intercept. So the intercept again now represents the average value for the baseline level. And if we have the treatment level, f2, in that case, we can get its predicted average by summing up the intercept and the slope. In other words, the slope represents the difference between the two levels, f2 and f1. All right, with that in mind, let's have a look at the model output of this fitted simple linear regression model. And what do we see? Well, we can see that in this admittedly artificial data set, the estimate for the intercept is exactly 0.8, which, as we know from this contrast coding, corresponds to the average for the f1 level. And the slope, beta 1, is minus 0.4, which means that the f2 level is actually at 0.4 because we have to compute the intercept plus the slope to get the average for the level f2. So I could express this as follows mathematically. I could say that my estimate, that's why I'm writing the hat symbol here, it's an estimate, not necessarily the true parameter value, but my estimate for the true mean of the group f1 is equal to my estimate for the intercept, beta 0, which here happens to be 0.8, okay? So that's my maximum likelihood estimate, if you wish, for this true mean of the group f1. And for the group f2, I would say that my estimate is equal to my estimate for the intercept, beta 0 hat, because it's an estimate, plus my estimate for the slope times, well, 1, so I leave it as it is, and this in this case is 0.8 plus minus 0.4. So the result, so I can write it explicitly, 0.8 minus 0.4, which will give me, you guessed it, 0.4. Okay, so that's how I can read off what the predicted average for each of these groups will be according to this linear model. And we can also verify this visually if we just create a descriptive plot of the group averages of the dependent variable. It will look as follows. I've already pre-computed this, so trust me, this is indeed the plot based on these data. And as you can see here, this matches quite neatly with what we have derived here. So we can see that for f1, the dependent variable, here it's called mean response time. So imagine, again, it's some psychological experiment, but it could be anything. We see it's indeed 0.8, and for f2 it's 0.4. Okay, so that's exactly what we could also read off the model output here. We have some error bars which represent either the standard error or the confidence interval, so we see some indication of what the variance is here around the group averages. And well, we can also draw sort of the slope which connects the average of f1 with the average of f2, so we can imagine this as a downward line, right? That's why it's a negative slope. And so we see that indeed there is a difference between the two groups, and as we see in the model output here, we have also a significant p-value based on this t-test that R runs automatically within this linear model. And that is, we can see that the slope is significantly different from 0, so that's one significant result. For a potential hypothesis test regarding this slope, right? That's usually the most interesting question to ask. But just in principle, there is also another hypothesis test that is being run here, namely the one that concerns the intercept. So here we also have a t-value for the intercept and also a corresponding p-value, which is also highly significant as we see. And maybe you've guessed it, this actually means that here R is running an hypothesis test on the intercept, which is basically testing the hypothesis that the intercept is or is not different from 0, right? So the null hypothesis would say, for this particular hypothesis test, that the intercept is equal to 0, while the alternative would say, no, it's different from 0. And here we see that it's actually very dramatically different from 0, and so this very small p-value reflects that, right? So high evidence to reject the null hypothesis that the intercept is 0 in this case. So if we want to write down a little bit more systematically what I just said, namely the two hypotheses, or like hypothesis tests that are being conducted here, we could say, well, on the one hand, we have one regarding the slope, okay? And then there's another one which concerns the intercept. And so for the slope, we can say the null hypothesis with this particular treatment coding would be that we expect the null hypothesis would say that there is no true difference between groups F2 and F1. Okay, so the true mean of F2 minus the true mean of F1 according to the null hypothesis should just be 0, meaning they are the same, right? And so in consequence, the alternative would be the negation of that, so saying that the true mean of F2 minus the true mean of F1 is in fact not equal to 0. It's something else, positive or negative. It's a difference, right? A real difference. And for the intercept, with this contrast coding, we would say the null hypothesis, which is being tested right here, is that the true intercept, which in this case means the true average for group F1, is equal to 0. And the alternative would be that the true average for the true mean for group F1 is not equal to 0, okay? And so with these particular data, the conclusion that we get is that, we have to reject actually both of these null hypotheses. So both the one regarding the slope and the one regarding the intercept, because in both cases we get a significant result, okay? Now, I'm making this so explicit here just because we will see in a moment that once we are considering different kinds of contrast coding on the same data, the hypotheses that we are testing are slightly different, especially regarding the intercept, as we will see. So we will see how really the contrast coding that we choose is closely tied to the hypotheses that are being tested by our linear model. Okay, recall what our contrasts had been in the example that we just saw. We can access them again using this command we also saw earlier. It was these treatment contrasts where one level F1 was 0 and the other level F2 was coded as 1. Now, we can also modify these contrasts. In order to do that, we can again access the contrasts, but now assign them new values. And in fact, the way we can assign them new values is just by specifying a vector which will contain the new coding for our contrasts. So we will maybe give F1 the value -1 now, as opposed to 0, but the value for F2 will still stay 1. Let's validate that and see if the contrasts have been registered. Indeed, now these are the contrasts that R has associated with this vector F. A small but crucial difference, because here we have now entered the realm of some contrasts. Some contrasts have the basic defining property that if I look at such a sum contrast predictor, the sum of the values that the individual levels have, in this case -1 +1, that's the sum, will be equal to 0, okay? Whereas for treatment coding, the sum of these values for the individual levels was not 0, in this case it was 1. For some contrasts, sometimes also literally called sum to 0 contrasts, the values for the different levels will sum up to 0. And this has important consequences, as we will see, on how to interpret, for example, the model intercept. So let's take our data again. Recall we had this data here that we are looking at right now. So we have our groups F1 and F2 and our dependent variable, and we have redefined the contrast coding for this categorical predictor F. So we can rerun the model that we had here and see what the output will look like given the new contrast coding, which is based on sum contrasts rather than treatment contrasts. So we are using the exact same formula. The only thing that's different now is that under the hood, this F is now represented as -1 versus 1 as its contrast rather than 0 versus 1. Okay, so we can execute this and have a look at the summary again. Now we see a slightly different output, right? So whereas before our intercept was 0.8 and our slope was -0.4, now we have an intercept of 0.6 and a slope of just -0.2. How can that be? I mean, our data didn't change. We still have the same data set, which, as we see here in this descriptive plot, has sample average for F1 at 0.8 and a sample average for F2 at 0.4. Well, it turns out that for some contrasts, for example, contrasts -1 versus 1, the intercept is now not anymore representing the average value of some reference level. Rather, the intercept represents now the grand mean. Okay, so the grand mean just means the mean over all individual data points, like on average. What's the average value of my dependent variable, regardless of any factor levels and so on. And with sum coding, the interesting property is that we will have the intercept represent the grand mean. So if we see this plot here, we can see that indeed if I imagine what the overall average is, abstracting from the difference based on factor levels, I would indeed see that that is exactly at 0.6, right? So that's now what my intercept represents. And the slope now just represents the step of going from the grand mean towards the level of the categorical variable which was coded as +1, in this case F2. So going from 0.6, which is the grand mean, towards the average, the group average for F2, which is 0.4, is in fact a step of -0.2. That's why the slope estimate is now just -0.2. Expressing this mathematically here, we could write our estimate for the mean of level F2 is equal to, well, the intercept estimate plus the slope estimate, okay? And in this case, this is 0.6 plus -0.2, so I might as well just write -0.2, and so this will give me 0.4. And the analogous way to obtain the group average, the estimated one for F1, is to say this will be equal to the intercept. And now, because this is coded as -1, I'll have to write minus the slope parameter estimate. And now this will be equal to 0.6 minus 0.2, okay, which is the same as saying plus 0.2. So this will be 0.6 plus 0.2, which will be 0.8. So we can see here that, well, we get to the same conclusion as before, like we can reconstruct our sample averages for the two different factor levels, be it with treatment contrasts, as we had seen before, or with some contrasts, only that the logic is now slightly different. So in this case, we are starting from the grand mean as a baseline, 0.6, and then the slope, as I said, tells us what's the deviation from the grand mean towards our group average. Whereas before, with treatment coding, the logic was that we pick one of the two groups, like one of the two factor levels, as our baseline and see what the slope then represented, what's the deviation from going from the baseline level to the other level, okay, to the treatment level. But either way, as we can see, we end up with the correct values, which also reflect our sample averages for F1 or F2. What also stays the same is the logic of what the hypothesis test on the slope represents. Well, okay, if we were really pedantic, we could say that, oh, in fact, now there's a slight difference because the slope now doesn't represent anymore the difference between the two levels, but rather half of the difference between the two levels, which is also equal to the deviation from the grand mean to one of the levels. So we could say, well, actually our null hypothesis now has changed in that it's now about half the difference between F2 and F1. So I could say the true mean of F2 minus the true mean of F1 divided by 2 is equal to 0, and accordingly the alternative hypothesis would be that it's not. But as you surely can tell from well, basic mathematical principles, is that if the half of something is equal to 0, then it's also equivalent to say that the original quantity is equal to 0 or is unequal to 0. So these are in fact just perfectly equivalent. That's why we can just sort of still work with this assumption, because that's in essence always true. When this is true, then this is true as well. But note that there is a real difference as far as the hypothesis test for the intercept is concerned. So recall that before, with treatment contrasts, the hypothesis test regarding the intercept was testing whether or not the group average of F1 was equal to 0 or wasn't, because that was what the intercept essentially represented there. But here, with some contrasts, the intercept, as we said, represents the grand mean. So now the hypothesis test is about whether the grand mean is or not equal to 0. That is the hypothesis test for the intercept, right? This one that gives us this t-value and this particular p-value. So we could write this as follows then. We could say H0, our null hypothesis, states that the grand mean, which at least in a balanced design, as we have it here, can be assumed to be the mean of group F1 plus the mean of group F2 divided by 2, right? It's kind of the average of the group means. That's only the case when the design is balanced, as it is here, where we have an equal number of data points for the two groups. And so the null hypothesis says this is 0, so the grand mean is 0, whereas the alternative would say the grand mean is in fact not 0, right? So it would deny the null hypothesis. And so here in this result from our linear model, we can very clearly see that both the hypothesis test regarding the slope, which was about, well, the difference between groups, and the hypothesis test regarding the intercept come out clearly as significant, meaning that we should reject both the null hypothesis that the group difference is 0, right? It clearly isn't. and also the null hypothesis that the intercept, like the grand mean of the data, is 0. It clearly isn't, like it's far up here at 0.6. It's not down here, right? So that's what these two hypothesis tests represent here. Now, the next type of contrasts we are going to see is just a slight adjustment to these default sum contrasts that we saw here. So here we had one level encoded as -1 and the other as 1, which resulted in the slope effectively being now the deviation from the grand mean to a particular level average. But there is also another thing which is called scaled sum contrasts, where the idea is that we now just have -0.5 and 0.5, for example, in this balanced design. And the idea is that now the difference between the contrast coded value for F1 and the one for F2 is exactly 1, which has a convenient property, as we will see when we fit the linear model again. So let's do that. We'll fit again a linear model and see the summary. And as we can see now, let me again rearrange the window, the slope now is -0.4, which is again the difference between groups as it was in treatment coding. But notice that the intercept is still 0.6, the grand mean. How did that happen? Well, the idea is that by recoding these sum contrasts as -0.5 and 0.5 instead of -1 and 1, the slope will now effectively represent the effect magnitude again, meaning the difference between the two conditions rather than just half of the difference. So that's convenient because that makes interpretation of the slope easier because it directly represents the group difference that we are interested in, like the difference between F1 and F2, not the difference between F2 and the grand mean, which is just half of that. So that's also a very convenient contrast coding. But everything else here stays the same, so we will still do an hypothesis test on whether the difference between the two levels is 0 or not, and also regarding the intercept, the hypothesis test would be just the same thing as for the unscaled sum contrasts, namely whether the grand mean of the data is 0 or not. Interestingly, here there's a small difference. So here now, when we want to compute the estimated group average for F1, for example, we would now have to say we take beta 0, so the estimate for beta 0, the intercept, and then, plus beta 1 times minus 0.5, in other words, minus beta 1 divided by 2. And here this would be equal to, what is our intercept estimate? 0.6 minus, and now the slope estimate divided by 2, so minus 0.4 divided by 2, in other words 0.6 plus 0.2, which gives us 0.8 as we expect. And likewise for F2 we would say this is equal to 0.6 plus minus 0.4 divided by 2, and this will give us, plus minus 0.2, so overall this should be 0.4, as we also saw previously with the other kinds of contrast coding. So as expected, we get the same predicted group averages as a result. 0.8, which we can find here, and 0.4, right? Here, we have so far just looked at cases where we have a single categorical predictor that we want to include in a linear model using some kind of contrast coding. But of course, we can also have more than one categorical predictor in our linear model. And for simplicity, let's say we have 2 of them. So we'll add another 2-level predictor here, which we may call G, which has the two levels G1 and G2, okay? And let's stay with the same kind of contrast coding for a moment. So suppose we would also use scaled sum coding to encode this G factor. So we would encode one level as minus 0.5 and the other as 0.5, assuming of course that these data are balanced. Now, if we want to include both f and g in the model, then we would also have to extend the model formula. So I'll maybe call this x and this y. So let me maybe rename the dependent variable here from y into z. And then this new linear model, which includes both of these predictors, would be, well, the intercept beta 0 times beta 1 times x. And then we'll also have to add another main effect slope regarding our second predictor, which we may call beta 2 times y. And then we will also have another slope, beta 3, which concerns the interaction between these two, the possible interaction. And this will be beta 3 times x times y, right? And then finally the error term. So you surely remember from stats 1 what an interaction is, I hope. So the idea is that, well, we can have main effects, which is just the overall effect of some factor, be it numerical or in this case a categorical one, and an interaction between two predictors is basically accounting for the extent to which changes in one predictor affect the magnitude of the effect associated with the other predictor, okay? And here, by using this full model structure, which accounts both for the individual main effects of, well, factor f in this case and factor g, and for the interaction, we are capturing possible interactions that might exist between these two. And with the contrast coding that we have specified here, it would be useful to think about how to interpret the main effects and interactions that would come out of such a model. So let's think this through real quick. So a main effect, for example, the main effect of the factor f can be interpreted as follows. So here in the model formula, this is represented by the beta 1 parameter, and applying this scaled sum coding, this beta 1 parameter will reflect the effect magnitude, that is the difference between levels f2 and f1, and specifically it will reflect the difference that we predict between f2 and f1 for the average value of g. In other words, the value where g is held constant at 0, because, well, the average of g, if it's also coded 0.5 and minus 0.5, is 0, right? So here we are predicting the overall average effect of f, right? When we average over the two levels of g, basically. And likewise, the same logic would apply for g. So for factor g, we have this this parameter beta 2, and here whatever effect magnitude we estimate here, which is represented by our parameter estimate for beta 2, this will be again the average expected effect, where we average over the possibly differently large effect magnitudes of g for each level of the factor f, right? However, if we were using treatment coding rather than this scaled sum coding, then the interpretation of the parameters beta 1 and beta 2 would be different, because in that case we would have for each of these two factors one baseline level and one treatment level, and so the baseline level would be encoded as 0 and the treatment as 1, and that for both factors. And so now when I look at beta 1, for example, which is the effect magnitude for the factor f, then this is the effect magnitude at the g value where g is held constant at 0, right? So the effect magnitude that I would basically estimate here with beta 1 would correspond to the magnitude of the effect of f when g has the level g1, right? And likewise, the effect magnitude we would estimate for g using beta 2 would be the one that's predicted when f is set constant at 0, meaning at level f1. So with treatment coding, this would now not be that, so beta 1 and beta 2 would now not represent estimates of like the overall average effect that we can expect for either f or for g, but rather the predicted effect that we expect, for example, for f when g is held constant at level g1, right? So that's the logic, how the interpretation of these parameters changes if we go from scaled sum coding, as we saw before, to this treatment or dummy coding. The magnitude of the interaction can be understood as a difference of differences. So if you remember, if we imagine, let's say in this maybe 2x2 table, we would write down the values of our dependent variable by levels of factor f and factor g. Then suppose we would find here there is a 10 maybe, and here there is a 20, here there is a 20, and here there is a 40, okay? So in this example, we would see that the effect of factor f differs depending on the level of factor g, okay? So for g1, the effect magnitude for f is just 10, okay? The difference between 10 and 20. But for level g2, the effect magnitude of the factor f is actually 20, so the difference between 20 and 40. So in such cases, when there is this difference in the effect magnitude of one factor, depending on the level of the other, we speak of an interaction, or like of a non-zero interaction. And what this beta 3 parameter would do, given this scaled sum coding, would be to directly estimate the magnitude of this interaction. For example, here the interaction would be 10, because we would take this difference between these two values, which is 20, minus the difference between these two values, which is 10. So 20 minus 10 is 10. So it's a difference of differences, right? And using this coding, for example, the beta 3 parameter would directly reflect the interaction magnitude. In this example, would be something like 10, okay? But we can first maybe change this to treatment coding. This would actually not change very much. So the same logic would apply. The beta 3 parameter would still reflect the interaction magnitude if we change this to 0, 1, 0, 1, okay? That is because the coding, like the distance between the two levels of the coding is 1 in both cases, okay? So minus 0.5 and 0.5, that's 1 unit away, and 0 and 1 is also 1 unit away. For all of these cases where it's just 1 unit away, the interpretation of the interaction parameter will actually not change. It will always yield the same values. But if we do something like unscaled sum coding, for example, so if we go and do something like this, then we have to be careful, because now when there is a difference of 2 between the two coded values for the levels, then the interaction parameter, beta 3, will actually just yield 1/4 of the interaction magnitude, right? So in this case, it would just yield something like 2.5 as opposed to 10 if we apply this coding. So these are all subtleties that we have to keep in mind when we are, applying contrast coding and then looking at the model output of our analysis. Because depending on which contrast coding we apply, we will have to interpret the numbers, like for the estimates that we get out of our statistical model, differently. And we really have to be sure about what they mean. And things like this can, of course, make a difference in how you interpret your model output. Next, we want to look at so-called repeated difference contrasts. Repeated difference contrasts are another, now a bit more advanced kind of contrasts, which are useful when we want to compare neighboring levels of a factor that has 3 or more levels, okay? So repeated difference contrasts might be useful, for example, if you recall the data set we had worked with earlier, which was about different doses of vitamin C. So we had a 3-level factor, small, medium, large. And now with repeated differences contrasts, we could actually do something that we haven't done before, namely to compare specifically if small is smaller than medium, like the dependent variable, and also whether medium leads to a smaller result on the dependent variable than the large dose. Okay, so we can compare always two neighboring levels of this factor. So this makes very much sense, obviously, only in those cases where there is this natural ordering of categories, right? There are other categorical variables where there is no inherent ordering. But when we have a dose, which is like small, medium, and large, it is very apparent that there is this intrinsic ordering, and we want maybe to account for that. So that might be a much more meaningful test maybe than what we did earlier, where we just used small as a reference level and compared medium and large to it respectively. It turns out that in the LinkPsych package there is another toy data set which is simulated data, right? Not real data, but which represents a very simple case of a 4-level factor, okay? And so for our purposes, we will suppose that this 4-level factor has some inherent ordering of its categories, which will make it justified to apply such a repeated different contrast coding scheme to it. So the dataset in question is called DF contrasts 3, and once we've loaded it, we can also have a look. Okay, this one's a bit larger than the previous one, but still very small, so just 20 data points. We can summarize them maybe, so look at the summary of this data set. And we see that there is, there's the factor, which is f again, which now has 4 levels, 1, 2, 3, 4. There's the dependent variable, whatever we might imagine that is, reading times, tooth growth, whatever. So these are basically the two things we want to relate with each other. We can also plot the data to see like what are the condition-specific means here. I've prepared that already, so this is what the plot of this data would look like. Let me enlarge it a little bit. And as you can see, we see that for condition 1, for example, or for like the factor level 1, the average value of the dV is exactly at 10. Then it goes up for factor level 2 to exactly 20. Then for factor level 3, it is back at exactly 10. And for factor level 4, it's high up at 40, okay? So this is the data set we're gonna work with now, and we wanna apply these repeated difference contrasts, which will basically ask, okay, hypothesis 1, is the difference between F1 and F2 significant? then hypothesis 2 is the difference between F2 and F3 significant, and hypothesis 3 is the difference between F3 and F4 significant. So these are the repeated differences for these pairwise comparisons of neighboring factor levels that we want to apply here. In R, in order to do this, there is actually a convenient inbuilt function. So maybe let's first check what our contrasts are right now. They are just basically treatment contrasts, not exactly what we want yet, right? Oops, okay, I have to specify the variable, of course. So these are treatment contrasts for a 4-level factor, not what we want here. We want repeated difference contrasts. In order to get them, we can use the function. Oh, I believe we have to load the MASS package first. And now we can use the function contour, like contrasts, dot sdiff, and then for this is the function which can automatically generate appropriate repeated difference, sometimes also called sliding contrasts for us. So we can do that and have a look at the contrast coding now. This is how it should look like for a 4-level factor if we want to have these pairwise comparisons. So now we have one like artificial numerical predictor which represents the comparison between the first and the second group, then one between the second and the third, and one between the third and the fourth, okay? We are not going to go into detail why these numbers allow for these comparisons mathematically, but this is how we can use it directly from the output that this R function gives us. All right, so with that updated contrast coding, it may be time to fit a linear model again. So we can do that. Let's call the LM function and say we want to fit a linear model of the dependent variable based on the predictor, which is F, with the data from the df contrasts 3 dataset that we just loaded. And maybe before we see the output, like a small quiz, can you guess what the estimates of the different parameters in the output should be, given that you already saw this descriptive picture of what the difference between 1 and 2 is, and the difference between 2 and 3, and the difference between 3 and 4 is? If you can guess correctly, congratulations. Let's see if you had the correct idea in mind. So if we now see the summary of this model, we can see in fact that, well, first of all, the intercept is 20, which here for repeated difference contrast just represents the grand mean, as we also saw descriptively here, right, in the summary. The grand mean of the dependent variable averaged over all individual data points is just 20, so that's what the intercept reflects for repeated difference contrasts, similar to sum coding. But here comes now the interesting part. So we see this first artificial numerical predictor, which is about the difference between the first and the second level. And here we get a 10, suggesting that the difference between the first and the second level is exactly 10 units. Then between the second and the third, we see a minus 10, suggesting that it goes down from the second to the third level by 10 units. And then we see the fourth level, the third predictor, which is about the difference going from the third to the fourth level. And here it suggests that there is a 30 unit upward difference. And we can verify that with, compare this to our descriptive means here for the different groups. And indeed we see, yep, that all makes sense. So we start here and then we go 10 units up. This is the 10 over here. Then we go 10 units down again. This is the minus 10 over there. And then from the F3 to F4, we go 30 units up again. So this is the 30 that we see here. So we see how these repeated difference contrasts yield estimates that match what we intuitively should expect as well by just looking at these group means in this plot here. Next, we want to look at yet another kind of contrasts, which is called Helmert contrasts. And let's see this again at the example of a 4-level factor, which could be, as we said earlier, different categorically defined levels of word frequency. And so Helmert contrast, let me write that really quick. The idea would now be, instead of, well, just now we had this this pairwise comparison of adjacent factor levels. That's not what we're doing here. Instead, we will say, well, take the first level, low, for example, and compare it against the average of all other three. So in that case, against the average of medium, low, medium, high, and high frequency. And then you are basically already done with this one, okay? Now you're only looking at the remaining three. So you go to the next one, and so the next contrast you will define will be about medium-low, and whether it is different from the average of the remaining two levels. So medium-high or high, right? And so then you're done with this level, and then the third and last contrast you define here is, well, the difference between medium-high versus high frequency words, okay? And then you're done, because then there is no other comparison left to make. So this is how Helmert contrast works. So they are kind of nested in a way. So you start compare low versus everything else. Then within that group, you start again and compare medium low against everything else. And within this, you then are only left with comparing the reading times or whatever the dependent variable is between the two remaining categories. There's also reverse Helmert contrasts, which work exactly the same, only that for reverse Helmert contrast, you would start not from left to right, but from right to left. So you would first take high and compare it against everything left, and then you would take the first three categories and so on. So reverse Helmert contrast and Helmert contrast are kind of the same thing, only that in one case we start constructing the contrasts going from left to right, and for reverse Helmert contrasts we construct them from right to left, okay? Back in R, we can again use our simple toy data set with the 4 categories to now apply Helmert contrast coding to it. So the way we'll do this is we will say contrasts of df contrasts 3, and then this particular factor f. That should be changed now to the following. So again, there is an inbuilt function which can create these contrasts called contour.helmert. And then as the argument, we'll have to specify the number of levels our factor has, in this case 4. Now, one thing to note is that with this inbuilt function, contour.helmert, we are constructing reversed Helmert contrasts. So these are actually the ones where you start creating the comparisons from right to left. So you first take the rightmost category and then compare it to everything else. Then you take from what's left the rightmost category and compare it to the remaining ones to the left, and so on. Okay, so that's a subtle thing to know, that this inbuilt function actually is about reverse Helmert contrast, not the original Helmert contrasts, which go from left to right. But anyway, so let's define these contrasts. We can also maybe have a look at them. We won't have to go into detail of why these contrasts yield this particular comparison. You can think about it if you want, but for us it's enough for now to just be able to define these contrasts using this R function. And now let's fit our model again and see what the estimates will be. So we can do this using the command as before, and we can see the summary. So one thing to note here is that, okay, I already mentioned these are reversed Helmert contrasts. So what is happening here is that F3, or what's called F3 here, basically, this compares the mean of F4, which was the rightmost category, to everything to the left, so to the average of F1, F2, and F3. Then this slope labeled F2 here actually compares F3 to the categories to the left, so the average of F1 and F2, and then this slope labeled F1 here, kind of unintuitively, I know, compares the mean of F2 against that of just F1. Okay, so that's how this right to left idea works here with the reversed Helmholtz contrasts. Another thing to note is that for the Helmholtz contrast we get from this inbuilt function, there's also some scaling going on, which is not so intuitive, which results in the, well, unfortunate fact that our estimates that we get here are not so directly interpretable. So here the difference between F2 and F1, for example, that just yields a 5, even though the difference is actually 10 units. So there is some kind of scaling going on with these inbuilt Helmholtz contrast you get from R, which has some mathematical benefits, but at the price of not being able to do a clear-cut interpretation of what these estimates are. That's just how it is. But we can still, of course, look at the result of the significance test and see which comparisons were indicating a significant difference. For example, here we see the difference between this large value for the fourth category compared to the average of the other three. That is significant, right? That also makes sense if we look at this plot. Like there's a huge difference between that one compared to the first three. Other differences, for example, the one between F3 and the average of F1 and F2, that is not really significant. So comparing this against these two is not significant, and also comparing F2 to F1 also doesn't seem to be significant. But if we consider the hypothesis test of the intercept, like asking if the intercept is significantly different from 0, yes, that is the case as well. Okay, so that's how we can interpret these results. All right. The last kind of contrasts we want to cover today are the so-called polynomial contrasts. For polynomial contrasts, the idea is that, again, imagine some predictor variable with multiple levels, let's say 4 levels or potentially even more, maybe 5 or 6 levels, like there's no limit, of course. If there's if these levels are somehow inherently ordered, as we also saw for the repeated difference contrast, for example, we could apply the repeated difference contrasts, but maybe we also have a bit more to say about these different levels, other than they are just ordered in a certain way. Maybe we have some idea in mind, which may be justified, that if I look at the 6 different levels, for example, that, and now here on the y-axis my dv, that there is some sort of linear trend. So it's not only the case that, oh, this one leads to a bigger result in the dv than this one, and this one a bigger one than this one, and this one a bigger one than this one, but maybe also the step size going from here to here, and 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 so on, might be similar. So if the step size is the same, roughly, for each of these steps, then we would indeed have some kind of linear relationship, right? So in the ideal world, it might look something like this. So we have some sort of linearly growing trend on the dv, depending on some consistent, or roughly constant step size for each step going from one level of the factor to the next one, right? So this is one thing polynomial contrasts can do, but actually they can not only capture linear trends, but also say if you have some sort of trend in the data which is quadratic, in the sense that it looks somewhat like a parabola, so something like it starts high here, but then it goes down, then it plateaus here, and then it goes up again. This kind of trend that looks like a quadratic function, basically, that can also be captured using polynomial contrasts. And you could even go higher and say we also want to see if there are cubic trends, so trends that can be represented by cubic functions, which would look somewhat like this, that you have some sort of S-shaped pattern here, okay, which resembles what a cubic function, like a function with x to the power of 3 would look like, right? And so these kinds of trends and also possible combinations of them, so linear trend, quadratic trend, and cubic trend, and possibly even higher order polynomial trends, this can be captured using the polynomial contrast. So this is a very powerful framework because we can not only capture differences between neighboring cells of the vector, but also constrain this even further to be able to find such linear trends or cubic trends or quadratic trends and so on, right? So let's see how we can apply these polynomial contrasts in our simple dummy example again in R, where we had this 4-level vector, and how the result will look like there. All right, so we are back in R. We still have our data set at hand here, which is the one with the 4 levels. And now let's change the contrasts of this vector f to polynomial contrast, right? Luckily for us, again, there is a corresponding R function that we can use. So we can just write contrasts of this vector. And we want to reset this to, and here comes the inbuilt function, contour.poly. And then as an argument, again, we specify the number of levels that our vector in question has. So we can apply that. We can check how the contrasts appear like now. This is the contrast matrix now. What you see here, abbreviated as L, Q, and C, actually stands for linear, cubic, and linear, quadratic, and cubic. So here, basically, we now have 3 different artificial numerical predictors. This is their specific coding, and this one will represent the linear trend that can be found in the data, going in this specific ordering of levels of the vector. This one will tease out the possible quadratic trend that may exist in there, and this third one will represent or be able to detect the possible cubic trend that might exist in this data. And so combining all these 3 trends together, we might get a representation of the actual data that we have, right? So with these contrasts defined as is here, let's fit our linear model again, shall we? So I should have the command still in the history somewhere. There it is. So let's do that. And we can again print out the summary of this fitted linear model. And we see these results here. And so what these results tell us at first glance is that, first of all, the model did indeed find a significant linear pattern in the way that the data is distributed if we go from the first level of the vector to the next one and then to the next one and so on. But also, on top of that, there is a significant quadratic contribution as well. And lastly, we also find a significant cubic contribution to the overall pattern that constitutes the data. If we look at them in these group-wise averages for each vector level plotted next to each other in the given order, right? And then, of course, there's also the intercept, which is significant as well, meaning it's significantly different from 0. And again, just like some of the other kinds of contrast coding that we covered so far, polynomial contrasts also has this property that the intercept has this meaning of being the predicted grand mean. So it's basically describing the grand mean of the data. And we see the estimate is 20 here, so that matches up quite neatly with our descriptive grand mean that we find in the data, which is also exactly 20. So that makes perfect sense, right? Now, with all of these results in mind, it may still be a bit harder to grasp what this actually means and how these different contributions, like the linear, the quadratic, and the cubic contribution to the pattern of the data, how they work together to constitute the predicted pattern of data that the model is assuming here. I think a visualization of this would help very much, so let's look at that now. There it is. So let's unpack what we are seeing in this plot. So on the x-axis we have the different factor levels, f1, f2, f3, and f4, and the y-axis is the scale of our dependent variable, right? Now we have a legend here which tells us what these different graphs are. So first of all, well, we have the intercept, which is just the straight line at 20. That's the intercept that our model found, right? The grand mean, basically. And here below, these three colored graphs are the different contributions. Like the linear contribution is this linear line, the orange one, that assumes this linear trend going from f1, one step to f2, and then to f3, and then to f4, right? There's always the same step size because it's a linear relationship. It can't be any other way. And then there is also the quadratic contribution, this lighter red orangey line, which is assuming this kind of quadratic relationship, like kind of looking like a parabola, okay? And then on top of that, there's also the cubic contribution, assuming this S-shaped pattern. And so what's happening here is that all these are added together, plus the intercept as well, and the result are the predicted values. So the predicted values, which are basically the sum of intercept plus linear contribution plus quadratic contribution plus cubic contribution, are here this black dashed line, okay? And as we see, the predicted values are very, very close, almost identical to our descriptive group averages. So using this polynomial contrast coding, we can very successfully recover this pattern of data, assuming these different contributions of linear, quadratic, and cubic polynomial order. Okay then, this concludes our first lecture on contrast coding. In this lecture, we looked at different kinds of default contrasts, so like contrasts that have a name that are typically used, that also exist as inbuilt R functions to some extent. In particular, we looked at treatment coding, the most basic one, sum coding, scaled sum coding as well, and then we also saw things like repeated difference coding, Helmert contrasts, and polynomial contrasts. In general, it is one thing to use these like off-the-shelf contrast coding schemes that have names and are like typically used for certain specific applications. But there's also a much more powerful and general manner to think about contrasts, which we will see in 2 weeks when we will have our second lecture on contrasts. Then we will see how we can define our own custom contrast matrices that are like specifically tailored for the set of hypotheses we want to test. And there is like an automatic procedure how we can get this optimal contrast matrix for our custom problem and set of hypotheses mathematically, right? This is something that's even more advanced than looking at these default contrast schemes that exist and that have names. But as you will see, it's actually a much more rewarding and powerful thing, because then you can really freely create contrast matrices that exactly suit you in the problem that you want to tackle. So that's just as a small teaser for what we're going to do in 2 weeks' time. For now, please study this material well and try to understand the logic and the philosophy behind why we need to encode categorical predictors using contrasts, and what the differences or different implications are depending on which of the discussed contrast coding schemes we apply. All right, so that's everything for today, and see you guys in the next lecture.